Imagine the frustration of trying to convey an idea or thought and having exactly what you want to say directly in your head. But when you open your mouth, the words get stuck or repeated until eventually your message is incomprehensible. This is the struggle of someone with a speech disorder. Hi, I'm Riya. I'm from Bay Area, California, and I'm so excited to share with you the project that I worked on with my mentor, Arij. And my project is called Epigenetic Regulations of the Intrinsic Properties of HVC neurons in zebra finches under stuttering. So I chose this project because I was interested in researching intrinsic plasticity, and I found that the cause of stuttering is unknown and research is currently ongoing. It seems like speech fluency is something that most people take for granted, and the difficulty of speech disorders is commonly overlooked. So this is the order that I'll present my research. And let's start off with some background. So, stuttering is a disorder of speech fluency that affects around 3 million Americans. And there are two major types: developmental stuttering, which occurs in childhood as a child develops language, and neurogenic, which occurs after a brain injury. But in both cases, the underlying neural mechanisms are unclear. To study these mechanisms, researchers in the past have turned to songbirds. And songbirds, like humans, rely on auditory feedback to learn and maintain their vocal output. So, for example, when a young bird learns its father's bird song, it creates this template that it gradually refines over time as it continues to develop. Just like how a child gradually refines the sounds that they make while by listening to their parents talk. So, common among many studies of stuttering, one of the ways that vocal manipulations of speech can be externally simulated is through delayed auditory feedback, or DAF. So, DAF works by playing back speech with a slight delay in live time of about 2 milliseconds, and this can induce stuttering like disruptions in both humans and birds, making it a useful model to study these topics. Additionally, the brain circuits underlying birdsong are well mapped. The HVC is the key premotor structure, and it's similar to the motor planning areas in humans. So here are a couple circuits that occur in the songbird brain system, and the HVC neurons are HVCRA, interneurons, and the HVCX, which are the neurons that I've analyzed in my research. So traditionally, changes in the brain circuits in sound systems were previously explained through synaptic plasticity. This is the strengthening or weakening of connections between neurons. But another mechanism, which is intrinsic plasticity, is just as important and is the focus of this study. So, intrinsic plasticity changes how excitable an individual neuron is by altering its properties of ion channels. So, voltage gated ion channels are proteins within the neuron membrane, and they open and close based on voltage electrical signals, and these generate action potentials, which are the signals of the neurons, and they're depicted by a spike. So the two of the main types of channels are sodium channels and potassium channels. And the sodium channels drive the upstroke of the spike as they open and sodium ions rush into the neuron, and potassium channels shape how fast the spike ends and how strongly it gains voltage before it starts another action potential. And this involves the potassium ions flowing out of the neuron. But the built-in electrical traits are called intrinsic properties. Now, this leads us to the research question. How does delayed auditory feedback alter the intrinsic electrical properties of HVC neurons in zebra finches? And what might this reveal about neural mechanisms underlying stuttering? So for my hypotheses, I have the null hypothesis, which says that disruptions in auditory feedback do not alter the intrinsic excitability of HVC neurons in zebra finches. And I also have the alternative hypothesis, which says that disruptions in auditory feedback fundamentally reshape the intrinsic excitability of HVC neurons, and suggesting that intrinsic plasticity plays a central role in speech disruptions such as stuttering. Now that I've introduced the goal of our study, let's go over the methods that we use to collect and analyze the data. So neuron voltages were recorded using single-cell current clamp recordings in brain slices in the HVC. To focus on the intrinsic properties, synaptic inputs were pharmacologically blocked. This means that the data was taken from an individual neuron and it was not affected by any synapses that were coming from neighboring neurons. So this data was collected by researchers in UChicago and the raw data was sent to me. And my analysis, the core of my analysis was done through Python, where I detected spikes and extracted key features to analyze them. So for each detected spike, a local window was extracted around the peak to isolate the individual action potential events. So this diagram shows a typical action potential. Throughout the graph, you can see the seven key intrinsic properties that I extracted from each of the spikes from each of the neurons to analyze for stuttering versus control. So we can see here, threshold, the start of the action potential. Peak is this star here, and it's the maximum voltage. The AHP, or after hyperpolarization, is the lowest voltage after the peak. And a couple more here are the width of the spike, the time to peak and time to AHP, and the spike frequency is taken by calculating the number of spikes divided by the period of time that current is applied to the neuron to cause the action potentials. So after I extracted all the data from the action potentials, I compiled them into data tables shown here. There's more data, but here's just a portion of them, separated by the control and stuttering, and each of the neurons, and each of the seven features. Now we can move on to the results. The central aim for my results was to highlight the intrinsic differences between control and stuttering neurons. To do this, I arranged the data into figures that makes the differences visually and conceptually clear. So let's take a look at the first figure. Here we have the firing of the stuttering neuron graph versus a control neuron graph. So here, the circles represent the thresholds, the green triangles are the AHP values, and the X's are the peaks. We can see immediately just by visually looking at it, the control neuron graphs have slower firing and they adapt as they move forward, which is shown through as between each spike, the space between gradually increases. On the stuttering graph, we can see that it's a lot faster firing, and some of the points, such as threshold and AHP, could be seen as unclear, as well as no adaptation. We can also see these observations in a different form through this firing frequency distribution graph. So in the control, which is blue, we can see that the firing frequency is generally a much lower, and there's a narrow distribution centered around 25 to 30 hertz. Then looking at, on the right, the stuttering neurons, we can see a lot more variable widespread with higher frequency, often reaching above 100 hertz. This next figure is a pair plot, and this encompasses all seven features that were extracted, comparing every single feature with every single other feature. Each dot here represents one neuron, with the control neurons in blue and the stuttering neurons in orange. Just by a glance, we can see an overall segregation between the two groups. So at this overview level, we can see that stuttering neurons are not just slightly different, but show a systematic shift in their excitability profile. But we can isolate and zoom in onto a couple of these graphs to draw more conclusions. Here on the top left, we can see a threshold versus amplitude graph. So the stuttering neurons in orange cluster with lower amplitudes and higher thresholds, and this points to weaker sodium currents driving the spike upstroke. This means that less sodium is entering the cell during the upstroke, leading to a shorter spike, as well as a spike that takes more voltage to reach the threshold. Then we can compare down here the AHP timing and depth. So here we can see stuttering neurons show a faster and deeper, more varied AHP, and this reflects stronger potassium currents. So this involves more potassium leaving the cell, causing the action potential downstroke to be faster and happen in a shorter amount of time. Now we can see here on the right a direct comparison of each property side by side. Here's another representation. We can look at the spike width and see that in stuttering neurons, there are narrower spike widths. And this is again consistent with the faster potassium-mediated repolarization or the faster downstroke. So to summarize the overview of these graphs, control neurons, they generate these big, broad action potentials with a slower recovery, while stuttering neurons generate smaller, sharper spikes with a faster recovery. And this shift in ionic balance, with the weaker sodium currents and stronger potassium currents, likely disrupts the precise timing that the HVC needs for its vocal control, and this is what causes the stuttering or vocal disruptions. I also did a statistical analysis on the data numerically. So for this, I used a non-parametric two-tailed Mann-Whitney U test. And I chose this test because it compares the rank order of values between the groups, rather than assuming this bell curve distribution. So in this test, the U statistic tells us how much the two groups overlap, and the p-value tells us how much that overlapping section, if it's statistically significant. So low p-value is a good thing. It means that the overlap is not statistically significant and the two groups come from different distributions. So looking at the results here, the intrinsic properties that I have highlighted in brown have p-values that are less than 0.05, which means that the difference between the control and stuttering neurons are significant or statistically significant. And here we can see also these two other features, time to peak and AHP, are highlighted in gray because their p-values are greater than 0.05, meaning that the overlap is statistically significant. So the two are from a similar distribution. This is an interesting result, especially for the time to peak, as that means that in the stuttering, the time to peak does not follow the trend with the rest of the stuttering neurons, where the stuttering neurons have faster firing frequencies and cluster together. The time to peak is actually longer for these stuttering neurons. So now let's discuss the impact of this study. So these findings demonstrate that neurons in the HVC undergo significant changes in intrinsic excitability when auditory feedback is disrupted. This indicates that DAF is not simply altering this network level communication of multiple neurons through synapses, but it actually reshapes the core properties of individual neurons. These findings could also influence how we approach human speech disorders. Stuttering is typically treated behaviorally through speech therapy, but if intrinsic excitability is a central factor, then, um, then it is possible for therapeutic strategies to one day be designed to modulate ion channel function directly. Together, these results offer new insights into both the neural basis of vocal learning and the potential mechanisms of speech disorders. Thank you for listening.
Thank you, Ria, for your again, very informative presentation. There's a question. You have multiple graphs and visual representations for your data. Were they hard to make? Was this a skill you had before your project or one that you learned for this project?
Yes, so I used a bunch of cat plots for my graphs, and I did that through Python, where I extracted the data from Excel spreadsheets and arranged them through the Python system. So this was not a skill I had before. Part of it was taught through my mentor, RH, and I had to learn how to code those different plots and how to arrange them. Um, to fit the images I wanted, like the colors of each of the stuttering and control neurons and all of that.
Oh, wow. That's a great skill that you learned during this project. What was the most like difficult part of your project?
I think the most difficult part for me was extracting all the components from the raw data. So the
Mhm.
raw data came to me in these data tables that had voltage, and I had to graph that over time. And referring to the graph, pick out the specific, I can show here, pick out mm, the specific intrinsic properties, such as spike width, spike amplitude. I think spike width was the most difficult for me to code, to like figure out how to find halfway between the amplitude. That's where the spike width is taken, and then like measure that with the code.
Wow. Very, very impressive. Very impressive.